Hello, this is ECE 637, Digital Image Processing 1, and today we're going to really launch into the technical content of the class. Last time I kind of did a brief inspirational overview of some of the computing that we're going to be doing, but I think a lot of that you're going to have to pursue yourself. I'll try to post more material online. One of the students was very kind to post some stuff on Piazza, so you might look there for information on how to configure your Windows machines. And I really do encourage cross-mentoring. So I enabled Piazza. Piazza, you can, if you're not familiar, if you're not a former Purdue student, I think Piazza is used pretty widely at Purdue. But if you're not from Purdue, you go to the web page and you click on that, and you can post questions and then get answers from other students. The TA. Oh, where's the TA? I think he's supposed to come to class. I think Wenry. I'm going to try to get him. Oh, there you are, Wenry. So Wenry, do you read the Piazza page? Yeah, Wenry will try to read the Piazza page sub, but we can't guarantee we're going to be able to answer all your Piazza questions, okay? It's mostly for you guys to communicate with each other, okay, because it becomes overwhelming, okay? So, but we'll try, all right? So you're going to try to answer questions on Piazza as best you can. And then, and you can always email us. You can always email me, I think, my emails. And if you want to talk for some reason, we can always set up a meeting. So, what we're supposed to, this is the syllabus. So I kind of didn't do what I would normally do on the second lecture because I wanted to go over some of the computing stuff, so you can see that. So let's pick up the pace today, and we'll start off with the continuous time Fourier transform. So now, I mean, I'll warn you right now so that you're not horrified that if you haven't seen the continuous time Fourier transform before, what I'm going to do is not enough for you to learn it. Okay, so don't panic. Don't say, "Oh my God, I can't believe it." So, yeah, okay. I'm basically reviewing it as if you've seen it before. If you haven't seen it before, you're going to have to go and do some remedial work. This is one of the 3 topics I talked about. This is the linear systems component, but I think most of you probably have seen it. The people who wouldn't have seen it maybe are people from anybody who hasn't seen it has seen essentially the same technical content but presented in a different kind of way. Okay, so like for example, if you were a math undergraduate, you would learn the Fourier transform, but the notation would be somewhat different typically, and your take on it would be just different. Okay, so it's almost like a cultural difference, technical culture. So you'll have to like make up that a little bit, and if you have problems with that, let us know. But I think it's very doable. So don't worry if it seems a little unfamiliar. But anyway, this is the Fourier transform, and oh my goodness, I forgot. I usually bring blank paper, and I forgot to bring it. This is the Fourier transform, okay? And this is the inverse Fourier transform. So basically, the concept of the Fourier transform is you decompose a signal into individual frequencies. And of course, all these notes are posted online, so you can, you have them there. But so the way to think about this is decomposing. This is like the analysis. You decompose the signal f of t into its frequency components, f of f. So for every lowercase f, I know there's a little bit of notational problem here because I'm using f for frequency, and it's also this function. But for each individual frequency, uppercase f of f is the complex number representing the amplitude and phase of that component. And then you can reconstruct the signal by adding or integrating together all the frequencies again. And so f of t is continuous time, also known as continuous parameter, and f of f is continuous frequency. So the frequencies here go from minus infinity to infinity, and time goes from minus infinity to infinity. So this is sort of the most basic transform in a sense, the continuous time Fourier transform. And then the associated signals that you use with the continuous Fourier transform these are like the standard signals that tend to show up. Rect, that's a rectangle. So if you, let me see, I guess I can do zooming here, right? Yeah, so the idea is a rect is equal to 1 here. So this is 0, and that's 1. And and the area under here, the width of that little pulse is 1. So the area under the thing is 1 times 1, which is 1. But it extends from minus 1/2 to 1/2. Now you might say, well, what's it equal to at 1/2? Well, according to this, it's equal to 1, but it really doesn't matter what it's equal to at that one point, because you're usually just taking these functions and integrating them against something. So the integral isn't affected by the value of just one at one point. And then this is the step function. So this function starts at 0 and goes to 1. When at 0, it's equal to 1. So it's just a step. People with a systems background know step functions are going to be really important, because that's how you analyze the behavior of linear systems. You put steps in them and you see how they behave. And then the sine function, well, the sine function and the step function look almost the same, but really they're different, because this is minus 1 and this is plus 1. So it's taking the sine of the function, and at 0 it's 0, because the sine's sort of undefined. Okay, now this is a really important function. If you're not like an electrical engineer, you may not have seen this one before. It's called the sinc function. And it's this screwball function that's kind of beautiful. That sinc, it's a sine pi t over pi t. Sometimes it's defined a little differently. There's small variations as how things are defined. Like, for instance, with the Fourier transform, I put a 2 pi in here. So by putting the 2 pi in here, then it turns out that f has units of cycles per second, or cycles, well, if there was time, if t was in units of time, then there would be cycles per second, or hertz. But you can also do it without the 2 pi, and then it would be like radians per second. So with the 2 pi, it's a little more intuitive. Without the 2 pi, it's a little more mathematically simple, you might say. Anyway, it comes up both ways. You just have to be careful about what convention is being used. But here I'm putting the pi in, so it's sinc t over t. So the sinc function is really cool. It's a really cool function, because why is this function really cool? Because why? Oh, I don't know. There's a lot of reasons, but we'll see later. The sinc function is like this. So 1, 2, 3, minus 1, minus 2. The thing to remember about the sinc function is, and that'll be 1. Okay. The thing to remember about the sinc function is that it crosses 0 at the integer values, except at 0. At 0, it's equal to 1. Okay. But every place else, it crosses like this. See, I'm not drawing it really that spectacularly well, but... And you have these things called side lobes, and they keep getting smaller as you get further out. Because if you look at it, if you look at the function, you have sine pi t over pi t. Well, what will happen is, sine oscillates between minus 1 and 1. So you're really dividing by t. So these things keep decaying by 1 over t, which is a little tricky, because the integral of 1 over t is not finite. So you can get some funny things going, but this is called the sinc function. And sinc function is very important because it's the Fourier transform of a rect. We'll see that in a minute. And then the other thing here is the lambda function. The lambda function is more like a local. Local, by local I mean that it's something I made up and a few people use. I think it's a little more popular at Purdue, but so not everybody will recognize this function. Everyone will recognize the sig function. That's like well known. It's universal. But this lambda function is something I use and the reason we use it is that it looks like a lambda, right? It's a little triangle, and a lambda is triangular, so it's sort of nice that that works out. And the thing about this lambda function is it's also got area 1. So it's like this. Yeah. It's -1, 0, 1. And then this is 1. Like that. So the area, it's a triangle, it's of height 1 and it's of width 2. So if you recall, the area of a triangle is the height times the width divided by 2. So this will have area 1. But the thing that's important is that this lambda function is results from the convolution of a rect with itself. So that's kind of interesting. It comes up to be useful. Now there's a thing, this is one of my favorite topics, but I'm not sure it'll be one of yours. Sorry, but it's cool. I think it's cool. Delta functions. Delta functions are cool because they're theoretically a little messed up. Things that are theoretically a little messed up are kind of fun because then they have these like paradoxical things going on. So what is a delta function? If you're an electrical engineer, you know about it because it's like a delta function, right? That's an impulse. And most fields have some kind, like if you are from physics, you would have seen this. If you're biology or something like that, maybe not. But the idea is this. A delta function, the idea is like, you have like a rect. So the rect goes from minus epsilon to epsilon. And the height of the rect is 1 over epsilon. So as epsilon gets small, as epsilon gets small, this thing gets really tall. And the area is equal to, hold on for a second, I got it messed up. This is over 2, I guess. So this would be epsilon times 1 over epsilon equals 1. And then I'd call this like, I don't know, delta epsilon of t. Now, and the idea is that if you have some kind of event, like if you have, for example, I don't know, 2 billiard balls. People know what billiards is, you know. So if you had, this is a billiard table. And those are the pockets. And you have 2 billiard balls. And the one hits the other. They're very hard, so when they hit, you get like an impulsive force. You get a very short force that's very high, and the momentum transfers between the two things. So, or if a hammer hits an anvil, that will create like an impulse. Of course, for the real physical process, this is always finite, but it might be large, okay? So mathematically, you'd like to be able to say that take the limit as epsilon goes to 0 of delta epsilon of t. Delta epsilon of t. You'd like to say this is delta of t. Unfortunately, even though you'd like to say it, it's not true. So it's intuitively true, but it's not really true. Because the thing is that if you take the limit, what happens is that if you take the limit, this goes to 0. So what happens is the function is equal to 0 everywhere except for at 0 where it's equal to infinity or it's undefined. So the integral of that function is 0. So the problem is that the integral of this is equal to 0, but the integral of this is equal to 1. So that doesn't work, okay? So the truth of the matter is that the interesting but perhaps sad reality is that the delta function is not a function. Okay, it's really kind of a shorthand notation for limiting behavior. So it's sometimes referred to as a distribution. So it's a shorthand notation for a functional that you get when you integrate it against something. So if you take the integral of delta t times g of t, what ends up happening is you evaluate g at 0 because you're multiplying the function g by this pulse. You're integrating, and then the only thing that matters if the function is continuous is its value at 0. So you take this limit, and that's what it is. Okay. So now that you know that, you can just pretend it's a function for the rest of the class, but it really isn't. Now, useful continuous time Fourier transform relationships. Okay, this is good. So a delta function has a continuous time Fourier transform of 1. That's pretty easy to prove. You just plug it into the continuous time Fourier transform formula, because if you put in a delta t for f, it'll evaluate this thing here at 0, and e to the 0. This is a bunch of junk, so you take 0, t is 0, so 0 times anything is 0, so e to the 0 is 1, so this integral is going to be 1. So that's simple enough. So the continuous time Fourier transform of delta is 1. Now, here's the thing that's kind of interesting. The Fourier transform and the inverse Fourier transform look almost exactly the same. You'd be like, well, what's the difference? Well, there's really only one difference, which is that here there's a minus sign and here there's not. So you take the complex conjugate. So that leads to what is called a duality property. There's a certain symmetry between the behavior of the Fourier transform and the inverse Fourier transform. If you know the Fourier transform of something, then you know you can compute its inverse Fourier transform pretty easily. So since we know that the delta has a Fourier transform of 1, we know that its inverse Fourier transform must also be actually the complex conjugate of 1. And since 1 is real value, that means its complex conjugate is equal to itself. So you get this relationship for free. But what's kind of interesting, I'll mention, is that if you plugged 1 in here and you tried to take that integral, you'd have a lot of trouble. Because you'd be trying to take the integral of e to the j 2 pi ft dt. For a non-zero f, this thing is just like an integral of a sine wave, which doesn't converge to anything. In fact, it's not absolutely integrable. So it just makes your head hurt. But there's a little bit of mathematical funny business going on there. But you could take the inverse Fourier transform. To make all this formally rigorous, it gets complicated. But it's basically true. I'm just pointing out that there's some issues that get resolved with advanced mathematics. But okay, now the rect function turns out to have a Fourier transform of sinc. You can actually show that pretty easily by just evaluating the Fourier transform integral. So and then by this duality property, the sinc turns out to be the rect. Okay, and now there's another property. Okay, we're going to learn in just a minute. Maybe these are out of order, which is that convolution in the time domain is equal to multiplication in the frequency domain. So if you convolve a rect with itself, you get this triangle function. I mentioned that earlier. You may not even know what convolution is at this point. Don't panic, okay? I'm going through this very fast for people who basically know it already. But if you don't know this stuff, you can go back and study some remedial material. It's not too bad. But the thing is that, so the convolution in rect with itself is a delta. So that means its Fourier transform must be a sinc squared. Okay. The interpretation of a sinc having a Fourier transform of a rect is important. I'll just mention it here. We'll see it again. But in time, if you have a sinc its Fourier transform is like this. Like that, okay? So if you take its Fourier transform, so this is f of t, and then f of f, the Fourier transform is rect of f. This is 1/2 minus 1/2. What this has an interpretation is that if you take a sinc function and you take the Fourier transform, it's a rect. That means that from an electrical engineer, the way they would look at this, if you have a signal that's a sinc, then it contains frequencies only in the fixed range from -1/2 to 1/2, and then no frequencies outside of there. So this is the impulse response of a perfect low-pass filter. Because if you convolve an incoming signal with this f of t, then that would be like its impulse response. You filter out all the frequencies above 1/2. Now you say, well, what if I want some other cutoff frequency? Well, you can adjust that. We're going to see that in a minute by adjusting, stretching or shrinking this thing. Okay. But the important thing to remember is this: whenever you have a perfect low-pass filter, its impulse response is a sinc. Okay. Whenever your signal has a perfect low-pass structure, and it's going to be a sinc like this. Okay. So that's sort of an idealized case that comes up a lot. Now here is the now there are properties, very, very useful properties of the continuous time Fourier transform. One is that it's linear. It's an integral, so integrals are linear, so it inherits the linearity of the integral. What does it mean for something to be linear? It means that if you take the Fourier transform of a times f of t plus b times g of t, you get excuse me, you get the Fourier transform of a times the Fourier transform of f plus b times the Fourier transform of g. Okay, this one's a little bit abstract but useful. If you take the complex conjugate of a signal in time, you get the Fourier transform flipped in frequency and complex in a complex conjugate. Okay, so this has an important consequence. If it's a real valued signal, then it's equal to its complex conjugate. So the Fourier transform of a signal and its complex conjugate, or for a real valued signal, the Fourier transform of the signal and its complex conjugate are the same. That means that this must be equal to f of f, which means that for real f of t, we have that f of f equals f star of minus f. Oops, f star of minus f. What does that mean? I do this stuff all the time, so it becomes second nature for me, but you have to get, it's like practice makes perfect, right? But if you have a signal and its Fourier transform, this is f, so you have the angle of f is always going to be conjugate symmetric. So that means if you take the complex conjugate of a complex number, its phase flips. You take the sign reversal, and its magnitude remains the same. Okay? So what ends up happening is the phase looks like this. The phase is always conjugate symmetric, like this. If it's whatever it is here, you flip it here, okay? But the magnitude, I'm running out of space. The magnitude is symmetric. So the magnitude of f is like this. I didn't draw it. Maybe I'm not as good an artist as I should be. That should be symmetric. So the magnitude is symmetric, the phase is conjugate is anti-symmetric. That's always true for any real valued for the Fourier transform of any real valued signal. Okay. That's an important property. What else we got here? Shifting. Oh, shifting is great fun. If you take a signal and you shift it in time, that has the effect of applying a linear, this is a linear phase modulation. You'd say, well, what do you mean it's not linear, it's exponential? Well, it's linear because this is the phase, okay? And you're taking the phase, and the phase is a function of frequency times a constant, t0. So that gives you a linear phase. It used to be, this is many, 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 many moons ago, when I was in graduate school or college or something, like when the dinosaurs roamed the earth. And there was a company that used to sell audio amplifiers, and they were called phase linear, okay? So that was sort of a sophisticated way of saying, we only introduce delays. We have no other distortions in our amplifiers, okay? So it's very, that was kind of sophisticated. I don't know. That would probably be lost on today's consumers. Okay, modulation. So, this is super important. So this is the conjugate relationship, okay? So it's the dual relationship to this shifting. If you multiply something by a linear phase in time, okay, then it shifts it in frequency. So this is super important, because if we didn't have this property, there would be no such thing as wireless communications. This is how you have wireless communications. You take the signal, like your voice, okay, if you're on a radio station, you multiply it by a very high frequency carrier, which is a linear phase modulation, essentially. Well, okay, so you're multiplying by a fixed frequency, and that shifts it up to a much higher frequency that can be effectively transmitted over an antenna. If you tried to just take your voice and amplify it on with an amplifier and put it on an antenna, it wouldn't go very far, okay? You wouldn't get much transmission because it's not impedance matched to the antenna. It doesn't go across free space. So that was the great innovation of Marconi, right? That changed the world, literally changed the world. That before that they would just use one wire, okay? So when they wanted, if you watch one of these old westerns, like a spaghetti western, like The Good, the Bad, and the Ugly, with Clint Eastwood, they had a telegraph where they go and every time they push the button, they make a contact or release a contact, and then they strung the wires all the way across the continent so they could send a message to California. Of course, that was revolutionary because before that it would take months to send information, right? But they go but they could only send one bit at a time, right? So they could either send a dot or a dash, which is basically a binary encoding. Oh, are we out of time? No. Oh, I got 20. Okay. So it's a binary encoding, right? Okay, but that's super inefficient for that channel. You're hardly sending any data. If you modulate the signal onto a carrier, now you can put thousands, millions of signals on that wire, okay? And that's what happens with Ethernet or with the fancy connectors on your iPhone, okay? So modulation is hugely important. Convolution is filtering. So if you have a linear time invariant, you have a filter. I talked about this a little bit. The input is f of t, and then it's a linear time invariant filter. We're going to talk about these a lot. And this is, we'll say h of t, and the output is y of t, okay? Then y of t is going to be equal to f of t convolved with h of t, okay? And convolution in time corresponds to multiplication in frequency. That's how come we can characterize linear time invariant systems by either their impulse response in time or their frequency response, okay? Or sometimes they call it the transfer function. So again, going back to the days when dinosaurs roamed the earth, if you bought like an amplifier when I was in college, they would give you a spec sheet with the frequency response, because that was considered kind of cool. And the frequency response tells you what the transfer function is. It tells you how much gain you have as a function of frequency. And a good amplifier would have very flat gain from, say, 20 hertz all the way to 220 kilohertz. That was considered really good. Okay. Multiplication in time yields to convolution frequency. This turns out to be important too, because this is the effect of windowing. We'll talk about that later. And the duality, I've talked about that. And then there's this thing called the Parseval's theorem, okay, which is basically inner products in space, in time, correspond to inner products in frequency. So what that practically means is that if f and g are equal, then this inner product becomes a norm, and in particular it becomes the energy. So energy measured in space and energy measured in frequency are equal. That's very useful in a lot of applications. We'll talk about it later. Okay, now that we went through the entire undergraduate curriculum of linear systems in a half of a lecture, now what we're going to do is we're going to talk about its generalization to space, because this is an image processing course. So you can generalize the idea of a continuous time Fourier transform to space, okay? And it's pretty straightforward. You basically, let's look. So here you have f of t times e to the j 2 pi ft. And here you have f of xy and times e to the j 2 pi. And you have two terms. You have u times x. So u is the frequency for the horizontal direction, x. And v is the frequency variable for the vertical direction, y. And the beauty of this is that because of the property of the exponential, exponentials have the property that e to the j, or I'm sorry, e to the a plus b is equal to e to the a times e to the b, right? That's a very beautiful result, which is super powerful, because if you write e to the j 2 pi ux plus vy, that's equal to e to the j 2 pi ux times e to the minus j 2 pi vy. See? You can separate them, and that means you can that relationship is very useful, because it means you can separate these integrals. We'll talk about this in a little bit. We can separate these integrals into two integrals, one over x and one over y. So the upshot is that the Fourier transform in 2D and in 1D are really very, very similar. So they share many of the same properties, okay? It's pretty direct generalization. Other things in 2D tend to be not so direct, but that's an example of something that's really pretty direct, and it's kind of nice. So now there's a lot of notational issues, because like what happens is in this space, there's like a collision between different notational standards that have developed in different communities, okay? And there's nothing I can do about it. So all I can do is explain it to you, and then you can be sensitive to it, okay? So normally when you plot a function, as a general rule, usually what happens is that x is this way and y is that way, right? Like in an undergraduate class, physics class or math class, this is what you do, right? But the problem is that it's a little different for images, because what happened is in the beginning of time, where time began in the 1930s, what I think basically at Sarnoff Labs, there was a guy named Armstrong. He and his friends at RCA, which is the Radio Corporation of America, more or less designed the standards for video. They basically invented television, is what came down to. They had already invented radio, right? They had FM radio and they had AM radio. They had AM radio for sure. By the way, of course, people still know what the word broadcast means, right? Yeah, okay, you broadcast, everybody knows what broadcast is, more or less. Maybe they won't in another 10 years, but you turn on, like you broadcast your radio stations, right? You're in your car, you turn on your radio, it's called broadcasting. Well, they used to do the same thing for TV. I don't even know if people realize, but you can put an antenna on your TV and get radio and TV stations, right, for free. You don't have to pay the cable company, although most of us do. But you know where the term broadcast came from? This is a good one, I think. Well, maybe you would like it. I don't know, but it's the farmers. It's It's an inefficient way of planting seeds where you just broadcast it. You just throw the seeds out and hope some of them germinate. Okay, so it came from. It was a farm culture. The United States was a farm culture in the 1930s. Most of the population lived on farms. So they had, it was a wild idea at the time to just spend all this money, develop all this technology, build the NBC. Okay, RCA started NBC. Build NBC to make all this production material. At that time, it was all live because there was no way to record it. That was why things like the Lucille Ball show were live. Okay, so what to just make it and just throw it out there for people to get for free, broadcasting. So that was a wild idea. We think that Google is wild and stuff. They were pretty wild back then too. Okay, that was very much like Google just giving away their search for free or open source software. You're like, how are you going to make money doing that? Well, they made a lot of money. Okay, so that's what broadcasting was, and they had to develop. So they had radio, and that was a big hit. Everybody listened to the fireside chats with FDR and so forth. But now they wanted television, right? So they're like, how are we going to turn this television? The idea of sending a picture over the empty space was just mind-boggling. Like, how are you going to do that? Send a picture, okay? So they're like, okay, well, we'll take this and we'll scan across the screen like this with a thing called a Vidicon tube, okay? And we'll draw the picture from left to right and top to bottom. I don't know why they picked left to right and top to bottom, but my guess is because you read English from left to right and top to bottom is my guess, okay? I mean, I can't prove it. Maybe somebody else can prove it or disprove me or whatever, but that's my guess. So what ends up happening is this becomes X and that becomes Y, okay? And then, of course, we have a third convention, which is really confusing. You have matrices, right? So if you have a matrix, this is like, so this would be, over here, this is F of sort of X, Y, I guess. But Y goes that way, and here you have F of X, Y. Okay, but Y now goes down that way. But over here you have like A of M, N, and this is M, and that's N, right? Oh, no, this is M, and that's N. Oh, it's totally confusing. So I just want to warn you, okay? I'm sorry. Again, there's not a whole lot I could do because we're not going to get rid of the notation of mathematics, and we're not going to forget everything we learned in calculus. And TVs this is how they're built. So it's kind of how it is. So you have to be a little careful about that. But in this notation, X is horizontal and Y is vertical. And depending upon your convention, it may either be vertical up or vertical down. And then U is the frequencies in the horizontal direction, and V is the frequencies in the vertical direction. Now, unfortunately, I wore the wrong shirt today. I should have thought of that. Usually, I end up wearing a shirt with pinstripes, like little stripes. Okay, so if you have something like this, and this is X. And say that's Y, it doesn't matter, okay? So if that's X, then this is, if you're going through this way, you have a lot of variation along this axis, right? But in this direction, you have very little variation. So what's going to happen, if this is U and that's V, this will have like a big spike here and a big spike there, okay? So this has high frequency components in the U direction, but not in the V. And so my shirts are like that. And then this would be the other way. here what's going to happen is you have something like this. This is V and this is U, okay? Right? So that's good. That gives you some basic intuition. Of course, if you rotate them like this, we're going to see later, then the rotating something in space will rotate it in frequency also. In fact, let's get to that. So now, okay, I spent a fair amount of time talking about the different functions. These are pretty much the same deal. There's only one thing that's different. You can have a delta function in 2D. You just multiply together two delta functions. So what ends happening is it looks like this. So this is X and that's Y. And you basically have an infinite spike at 0 here. You have an infinite spike at 0, okay? So that's a 2D delta. And remember, the area under a delta is 1. So the volume in this thing is 1. So if you integrated 2D, it integrates to 1. You can also have a rect. A rect looks like this. I'll just draw over it because, a rect looks like this. It's a little square. By the way, that is not isotropic. Isotropic means that it behaves the same regardless of angle. So if I rotate this, this obviously looks different. Now, of course, the axes look different, but forget about those because those are just coordinate systems. But the actual object is a square. So if I rotate it, it looks like a diamond. A diamond and a square are really the same shape. They're just at 45-degree rotation. So this is not isotropic, okay? Sinc function is just a 2D sinc. We'll see what that looks like. That's also not isotropic because it's the Fourier transform of something that's not isotropic. But there is a thing called a circ, which is isotropic. A circ looks like this. It's a circle. It's like a disk. And inside the disk, it's 1. And outside the disk, it's 0. Okay, so that comes up a lot, particularly in things like optics. Because if you have a lens has, a circle. You know what a lens looks like, right? I'll bring my camera in. It's fun to play with. And it's got an aperture. And the aperture is typically a circle, or it approximates a circle. Sometimes what they'll do with an aperture is they'll have like, if you've ever seen it, they'll have like a little, it's like, they'll have like an iris, which is like this. Little plates of metal. So that, this is the interior here. So they'll use a polygon, essentially, to approximate a circle. But it's pretty close. So, and that way they can change the aperture by moving these little plates. Right? That's a kind of a standard technique. So the circ comes up a lot in optics. And now, if a function has the property that f of xy is equal to g of x times h of y for some g and h, then it's called separable. And separable functions are very useful because they have a lot of properties which make them easier to manipulate. So the point is, so this is like a yes-no quiz. Is that function separable? Yeah, obviously, because I've just written it as a combination product of two functions. Is that function separable? Yeah. Yep, separable. Is that function separable? Yep. Is that function separable? No, not separable. So this is not separable, but it's isotropic. Okay, because the circle has the property that if you rotate it, it looks the same. Okay? And that's useful. The 2D Fourier transform inherits many of its properties from the 1D Fourier transform. Linearity, that's pretty much the same deal. Conjugation is pretty much the same deal. We'll see that there's some subtleties here because the symmetry's a little bit more complex, but we'll talk about it later. Okay, but it's the same concept. Scaling. If you take a signal and you scale it, you stretch it. If you stretch a signal in time, you contract it in frequency. Okay, so, I like to give this example. I have to because it's too much fun. Does anybody know about, like, I don't know, they may have heard, like, in ancient times, maybe when their parents had this thing. It was called a record player. Have you ever heard of a record player? Okay. where you have this little piece of vinyl plastic, and it has a little thing in it, and as it goes around, it makes the needle vibrate. They actually, the first one, Victrola, which was bought by RCA, the Victor Corporation. In fact, RCA's thing, their like logo, was a picture of this dog listening to his master's voice. Was the thing that because the idea was that Victrola was supposed to sound just like a real human. Of course, it didn't sound like that at all. How many people have ever heard of Victrola play? They really sound, you know how like the old music is like, that's because it was recorded on a Victrola, because the frequency response is terrible, okay? But anyway, they would actually mechanically do that. There was no electronic amplification, okay? So, of course, modern record players have amplification. But you can put your finger on this thing and slow down the rotation speed. If you do that, you're stretching out the signal. And what happens to the frequencies? They go down, okay? And, of course, now they have, like, electronic simulations of this actual physical analog thing that they use for, you know, places that are, what would you call that? Help me out here. A place to listen to music. They have things where you put, like a DJ, right? So a DJ would come and they'd put their finger on this electronic thing that simulates the actual vinyl record slowing down. But the point is, when you slow it down, the frequencies go down, okay? And when you speed it up, the frequencies go up, okay? So you get higher frequencies from when you contract this thing. So stretching in one domain causes, stretching the signal in time contracts it in frequency. And contracting the signal in time stretches it in frequency. They go in opposite directions. Just memorize that, because you will get confused on this point. For some reason, it can be confusing when you're really in the throes of battle, okay? I don't know exactly why, but for some reason, I mean, I always get confused about it. It's sort of, you just best to memorize that relationship, that they're opposite. So that's stretching. Okay, shifting, we talked about that. Modulation, convolution, it's all the same. Multiplication, same. Duality, same. And Parseval's theorem is the same. So all those things are pretty much the same deal. But there are a couple things that are different in 2D. One is separability. If you have a separable function, then the Fourier transform of the separable 2D function is the product of the 1D Fourier transforms of each of the two functions. That's very useful. And the other thing is that this crazy rotation relationship, which we'll talk about. Basically, that's saying if you have two signals, one in time and one in space and one in frequency, if you rotate one, the other one rotates. So they rotate together, okay? That's more or less the upshot there. So here is the, I have like a minute and 44 seconds. So this is this proof of the separability relationship. You can go through it. It's a straightforward proof, okay? But basically, it leads to another thing, which is that the continuous space Fourier transform itself is separable. What does that mean? It means that, okay, well, no, this is the separability of functions. Okay, I'm not. So what happens is that, yeah, if the function is formed by the product of two functions, you can show that you can write it as the Fourier transform of each of the two functions. So here are some Fourier transform relationships. If you have a delta in 2D, okay, then its Fourier transform is 1. I just wrote 1 because it's hard to plot the function 1. Okay, if you have a 2D rect, its Fourier transform is a 2D sinc. Okay, and if you rotate a function, this is a rotation matrix, then what happens is the rotation in space and time corresponds. So let me just show you the final result. Go through the slides and do the calculations. So if you rotate this rect function, you see that's rotated, then the sinc function rotates. Here, this is a contour plot, so it's easier to see. Here, this is a diamond now instead of a rect. And this rotation, this sinc function is now rotated by 45 degrees. Okay? And now this is the case of a circ. We'll finish the other thing next time. that here you have a circular function, so here you have a, we'll talk about it next time. Okay, so thank you. See you next Wednesday.